Yes, fine. Just let's recall. We have been discussing on statistical decision theory, where regression was the topic of discussion. Concept of regression, we have been broadly, trying to introduce this. Okay, where we have took the examples of linear regression and KNN example. Okay, as an example, we have considered that. Here, the point that has to be noted in the previous discussion is that we are trying to come out with certain mapping function f, which maps the input space to the output. That input is the uh, data which is represented by a p-dimensional RP space, okay, to the output real space. Okay, so that's a mapping function. That so we are trying to devise this mapping function, and the idea is this. This is an example of a linear regression, which today we will be elaborating further anyway. And there is an example of a nearest neighbor classifier. That's also we have seen there. But the point here is, what is the performance measure that we consider? So we have addressed the loss function. So loss function is basically the function which compares the true output y and the output of the function f of x. F of x is the output of the function. So it compares and gives a certain loss function. So f of x, you may call it as a predicted value or estimate of the input x. When you give a input x, then the system, the mapping function, gives the output as f of x, and that may not be the true output, and there exists a certain difference, and that is we are trying to quantify using the loss function, and particular loss function that we have been discussing for a regression case in general. Okay, for a regression case, so that's a squared error. Okay, so what squared error basically indicate what it is the equal to the difference, the square of the difference between the true output and the predicted output. Okay, so that's important point to be understood. Okay, and we have defined what is known as expectation mean squared error, or rather clearly it is expected prediction error, EPE we have denoted as, which is nothing but squared error itself, but the expectation of the squared error. When it becomes a random variable, you understand that so this expectation comes into picture, and the mean of this is quantified by expectation. Statistical tool that we use is expectation, and that if you simplify, and if you require a joint PDF as we have discussed earlier, and you can finally come out with what is known as the function. So before that, the minimization of that, so we have to understand one point here. So we come out with the EPE function, and the objective is to come out with a function f such that it will minimize EPE for all values of x. Okay, or all inputs for every value, every point in x. So the function must be such that to minimize this error. The minimizing error is our goal. So that we have done it here. I'll just go through, yeah, this particular expression. So argument minimum we have used. Okay, so if you look at this equation 5, okay, f of x, so we are trying to bring out that mapping function f such that it minimizes argument minimization of conditional expectation of y given x, expectation of y given x. So y minus c the whole square given x is equal to x. Capital X represents the random variable of the input, and at value, certain value small x, x at a point. Okay, so the output at that point is f of x, which is denoted here as a c, because we are going to find out that value of c which minimizes this RHS, which minimizes this part, and therefore you do it for all values of such x, entire values, and you will come out with the function f. That's what the argument minimum indicate. So that's a quite important uh, expression to understand. And once you have understood that point, finally we write equation 6 here. So that is f of x is nothing but, it is the same thing, equation 5 just rewritten. Expectation of y given x, sorry, expectation of y given x is equal to x, that is at the point wise. Okay, so this prediction is known as conditional expectation or regression function. It is quite important to understand that it is a regression function. Okay, so we have, having understood the regression function, now we shall move on to a linear regression, an example of a linear regression. I hope there is no question as so far. So we have done this in the previous class. Further, right, linear regression. So this is one of the example for the regression uh, problem. So linear regression, as the name indicates. So what is linear here is IO expression is linear, input output is linear. Okay. So we know that f considered, IO expression basically it's a mapping function. F is considered to be linear in this case. So we know this expression, equation 1. Let us look at this once again. F of x equals beta 0, beta 1 into x1 plus so on up to beta p into xp. Here what actually betas represent and x1, x2, etc. represent. So betas are the coefficients. Essentially this represents the betas, represents beta 0, beta 1 and so on up to beta p. This represents the coefficients of linear regression. Coefficients, correct? And x1, x2, etc., xp. So these are the points drawn from the input space data, input data, and it corresponds to one particular data point. More compactly, we can represent this equation 1 using in the matrix form. Actually, this is not exactly the matrix form, but it's a kind of a vector notation, we can say, a partial, of course, representation in the matrix form. That's a different notations that can be given. Maybe here it is written like the vector x transpose, T denotes transpose here, x transpose into beta, vector beta. The beta is here, that is b0, b1, etc. up to bp. Okay, so those are the coefficients, b0 to bp. This is denoted as, column vector. It's a column vector. Usually when we usually say vector, it is column vector. You understand that in order to get equation 1, then I need to multiply this x vector, which is x0 to xp, it is written here in the vector form, I mean column vector, with of course x0 is equal to 1. So if you multiply that x transpose into beta, you will get this equation f of x, is it not? That's very trivial, but maybe what I'll do is, it's better that later we will represent as x as a matrix, and maybe it will be convenient if I write it as a row matrix or row vector rather than the column. Though it's a right way of writing it, I'll just change this. Okay, please bear with that. Okay, I think in order not to confuse, I will write down this now itself very clearly, that x, let me write it as column, that is x0, x1 and so on up to xp. I'm writing it as a column vector, that's all. Okay, I think with the, of course, x0 is equal to 1. Now when I do that, this is not transpose now, this is simply uh, x into beta. So vector x into vector beta. I will tell you why I have done that in the next we will understand. I hope equation 2 is still valid, because in terms of matrix, what is the dimensionality of this? This dimensionality is what are the number of rows? It is 1 into what are the number of columns? It is p plus 1, is it not? P plus 1. What about the dimensionality of beta? How many number of rows are there? That is p plus 1 and column 1. So you can multiply these two and you will get the equation 1, okay, after multiplication. Fine, that's fine. Now let us get into the matrix x. So what is x here denotes? Before that, the small x, vector x denotes a data point. You have to understand that this entire thing represent one data in the input space, because x0, x1, etc. represents actually the different features of the input. I mean, feature, it represents the different features, or the what we call it as attributes, maybe like age of a customer, or another variable may represent the salary and so on. So these are the attributes, or we call it as a features. So how many numbers of features that we have? Actually, there are p number of features, but then x0 is equal to 1. x0 is equal to 1 because we have introduced this beta 0 in this equation 1. It's not introduced, it is existing because of the for the any linear equation which represents actually the y-intercept. It's a y-intercept, right? Constant value when you add in a linear equation. So it is a y-intercept that you have. So in order to write it as a single summation, we understand that we have to take this x0 equal to 1. So therefore, x0 is simply 1 for all the input data points, and x1 to xp represents different features. Hope that interpretation is clear. Now we shall write down the different data value data points of the matrix x, or in the matrix form we shall write down the input. So x is equal to the first data point. This represents, this first row represents the first data point, x10, x11, x12 and so on, x1p. Second, of course, represent the second data point, x2p. Say there are n number of data points, x say capital N 0, next is xn1, xn2 and so on up to xnp. So this matrix represents the input data space or input entire data set that you have. Okay, so what is the dimensionality of this matrix? How many number of rows you have? N into number of columns, that is n by p plus 1 columns you have. Hope that is very clear. Now that represents the input space, as I said. Now what about beta? Beta will remain same as what we have said earlier. What is beta? Let me write down beta for clarity here once again. Beta is, that is not changed. Beta 0, beta 1 up to beta p. Okay, beta p. So this will remain same as p plus 1 by 1, correct? That's the dimensionality. Okay, now let's see what is the expected probability of error, EPE. That is actually the squared error that we are talking about. Earlier we have already seen this in the case of regression in general. Now we are coming to the linear regression in particular. Okay, so in the linear regression case, the error probability or the expected probability of error is essentially same as the squared error. So we have uh, already represented squared error, right? Earlier squared error, which is nothing but earlier y minus f of x, we did this whole square. We know this, correct? What is f of x? It's a predicted output or the estimate of the output that you have. Okay, now that the same thing in the matrix form, y becomes actually the matrix sorry, vector y. Here y is a value earlier that we have discussed. Now it is a matrix or rather a vector. What is the dimensionality of y here? Y is a vector. So let me write down here. Y is y1, y2 and so on up to yn, isn't it? So it's n by 1, correct? There are n number of data points. So for every data point input data that you have, the corresponding output, like for x1 it is y1, x2 it is y2 and so on, right? Now the squared error, which is given by the equation 3, hope it's clear. So vector x, this x represents the matrix here. I denote it as a double bar here, double bar, x bar bar. So that represents the matrix in my notation. And beta is a vector, right? Beta we know. So beta is essentially, it's not a, I don't consider this as a row, it's a column actually. I think it's better that I represent, I already done it here. Okay, so please consider it as a p plus 1 by 1 matrix, or it's a column vector. So this y minus x beta cap square is the error probability or probability of error. That's for the linear regression case. Now what is the objective? See, we have to come out with the f of x, or rather coming out with the f of x is same as finding the values of these betas, coefficients. So our objective is to compute the betas such that this will minimize the error. Equation 3 has to be minimized. Okay, so that's what we do here. So equation 3 can be minimized to find out the value of beta. Okay, now how to find out how to minimize this? When you have such an equation, it is actually a quadratic equation. If you look at it, it's a quadratic equation in betas that you have. So it has a minima, it can have a maxima and minimas, but the number of minimas may be more, but at least one minima is guaranteed because it is a quadratic expression. So how do you find out? You have to find out by taking the derivative and equating it to 0, is it not? This is well known for all of us, I believe, that to find out a minima of any curve, so what you do is you derive with respect to the whatever you are looking for. So here it is beta, so differentiate and equate it to 0, so that will give you the minimum value or corresponding to one of the minimum in the input curve, right? So that's what we do. And if you do that, that is equation 3. So differentiating with respect to beta and equating it to 0 and solving it for beta, that would essentially give this beta cap is equal to x transpose into x the whole inverse into x transpose into y. Maybe in the beginning it may be little difficult to understand this particular point, right? uh, let me just try to elaborate this. Maybe you can do it. I think you may be good at this. It's just a matrix operation that we have. So equation 3, let us find the derivative. That is, what you do is differentiate equation 3. You can do it parallelly, okay, with respect to beta. With respect to beta, that is actually partially we write it as dou EPE of I here write it as f cap here. I'll tell you, cap basically indicates the estimate. Okay, dou EPE by dou beta. That is, with respect to beta we differentiate. That is actually dou by dou beta of this y minus x beta, right? The whole square, of course. This is a squared error. Squared error that we have. So it's a differentiation with respect to beta we do, and then equate it to 0. This is not. So here y is a vector, x is the matrix, beta is a vector. So we have to be careful about the dimensionalities while writing down. So squaring this is essentially same as dou by dou beta. So you have to multiply by the transpose into itself, right? That is y minus x beta, the transpose into y minus x beta. Okay, y minus x beta is not. So this gives what? The square. So it's actually you have the resultant, whatever the operation inside, that will give you some matrix. Look at the dimensionalities, you can follow it later, you work out yourself. So when you square it, it's same as multiplying in the matrix operation, transpose into that matrix itself. Okay, that's a squaring operation. Now here it is a plus b into a plus b, you have a plus b the whole square, or rather a minus b the whole square. So a simple operation, dou by dou beta. So you multiply this respective terms, y transpose into y, isn't it? Y transpose, first term y transpose into y, and second term, maybe if you write minus, so when you multiply the x beta into y, and another here minus, this is minus x beta, actually minus x beta into y, another one is here also minus x beta into y here. So it is 2 times. So you can write it as 2 times, it is beta transpose, is not, beta transpose into X transpose. The order we have to be careful here. Y, X transpose into Y. In order to write, just to verify this order is correct or not, what you do is find the dimensionality and matrix multiplication. Is it correct or not? Just check it out. So next is the last term that you have here, that is plus minus into minus. So it's plus beta transpose into X transpose, the first one X transpose into X beta. X beta. So this is the just elaborated version. Hope you are following it. To minimize, the objective is to minimize this. So what you do to minimize, okay, you set the derivative to 0. Set derivative to 0, and then evaluate for the beta, right? So that if you do, so what we are doing is this particular expression what you have, maybe equation A or whatever you call it as, this you set it to 0. That is dou by let me rewrite if required, dou by dou beta into Y transpose into Y minus 2 beta transpose into X transpose Y plus beta transpose X transpose X beta. So this, if you differentiate and equate it to 0, so then what actually you get, I mean, if you simplify, is a estimate of beta, not actual beta, but the estimate, right? Because the minimum value, correct? So you may represent it as now beta cap. So what I'm trying to say is, if you differentiate, first term will not be there. So second term is minus 2 times. So we are differentiating with respect to beta, correct? So X transpose into Y, beta will vanish. And next is here it is beta transpose you have, right? So X transpose into X you have as it is. So this would become 2 times, because beta transpose into beta 2, right? So it's like a squaring operation, plus 2 times it is, say, X transpose X into beta. The order, please uh, bear it, just find out whether it's correct or not. You have to find out from the dimensions. Fine. X transpose into X into beta. So now that is equal to 0. Now we call this as beta cap. That's what I'm trying to say. What beta cap represents? Beta cap is the estimate of beta, or the prediction of beta, predicted value of the coefficients. So if you just look at it, so here 2 cancels, and X transpose X into beta cap is the same as what is that? It's same as X transpose into Y. That's fine. And taking the inverse X transpose into X, the whole inverse, if you multiply, you understand that you will get a beta cap, which is on the right hand side. So X transpose X, the whole inverse, into X transpose into Y. Hope that is clear. So this equation, which we have written as equation 4, beta cap is equal to X transpose X, the inverse, into X transpose into Y. So that's what the equation 4 is. So that's how you get it. Here one point that has to be noted, or we have assumed here, while taking this inverse, it is assumed that the inverse exists. That means this X transpose X is you know, uh, the whole universe of this exists. The whole universe exists. This is assumed. It's a non, or you can say it's a non-singular matrix. It's non-singular. Correct. So that the inverse is so this assumption is not very poor or not valid kind of thing. So it's a assumption is fine because you're taking the input space and taking the square of it, and its inverse can exist, and so beta cap can be computed. I hope the steps are clear. So that is what the computation of the estimate of the coefficient of the linear regression. So what we are trying to do here, we are trying to estimate the coefficients of the linear regression. Actually, later we'll understand that what we have done is a multiple regression uh, because there are multiple input variables. It's not a one variable that you have. You have x1, x2, and so on, xp. So multiple input variables. So it's also known as multiple regression kind of thing. Fine, this steps are fine. Then we shall move on further for the classification part. If there is any questions, I can take it now. Right. So moving on further, let's get into the classification part. So far we have been discussing on the regression. Okay. Now the problem is classification. It's like a counterpart of this regression that we have been discussing on. This another type that we have. Now in this case, what is the input? Input is same as the input that we had earlier. So x, input x is a matrix. What is the dimensionality of the input matrix? That is n by p plus 1, is not? N by p plus 1. So this belongs to RP space. So once again, what actually in the so let me just come back to this. I wanted to mention one point here. So in this matrix, what exactly the rows represents? The rows represents, it is a individual data points in the input space. You're getting it? Though how many data points that we have? N number of data points that we have. What does the column indicate? Column indicates the features, individual features. Okay, how many number of features actually you have? Actually, you have p number of features, but then first column is all ones, and therefore it becomes p plus 1 columns. I hope that point is clear. So remember, always the columns represents the individual features, whereas the rows represent the data points. So these data points can be represented as a point in p plus 1 dimensional space. Is it not? So one data point, if you consider one vector here, okay, or one row rather, one row. So this row is a point in p plus 1 dimensional space. This is another point. So how many such points are there in that p plus 1 dimensional space? There are n number of points that you have. So n number of data that you have. Hope that visualization is you are getting it clear. Now we have to make it more concrete at this stage. Able to visualize properly and imagine, and things must be properly set. Okay. Coming to the output. Now let us denote output by G. Okay, something different from previous Y. Okay, so we are using some different variable. That's all. So it belongs to not a real space. Earlier we said, if you remember, just to recall, y belongs to some r, we said real space. Okay, so this is in the earlier case, this is the case of regression. Okay, but now this is a difference that you have. We say that it belongs to some xi which is not essentially the real space, but it is a discrete set of values. Xi represents a discrete set of values. Okay, it's a discrete space, you can say. Okay, because the output is a it's a classified it's a particular classes. You have number of limited, I mean finite number of classes. Output is a finite, output has a finite number of classes. Therefore this G is drawn from a discrete space. Hope that point is clear. So if you just look at your training data set, so this should essentially look like x1 g1, x2 g2, and so on. Something like x, suppose a n number of data points that you have, xn gn. What actually g1 g2 etc. g1 g2 etc. represents it, it belongs to this discrete space, one of this. So there is a finite number of values which are already defined, and so g1 g2 etc. belongs to one of them. Okay, so x1 can be a vector actually. X1 is a vector, x2 is a vector, and so on. So x1 vector represents the data point 1 x1, data point x2, and so on. Now coming to our goal or objective, so we again try to learn a function f such that it maps now from a p-dimensional real space to a discrete space, discrete space, say some xi. Okay, so it's a mapping function that you are going to learn. So that's what we are going to do now. It's very similar. The procedure, if you look at, it's very similar to that we did in the case of regression. So the procedure is almost same. Now let us look at, in order to set our f of x, the theory. So we need to look at what is our performance measure, correct? So performance measure, or basically the loss function that you are looking at. So earlier, what was the loss function? So if you remember, it is a squared error. So now the squared error exactly cannot be considered. The reason is very simple. Output is not continuous. Because the output is not continuous, you cannot exactly look at the squared error for every point. Okay, so it should be something different from that. Okay, so what is important is to set the loss function here. So here we define something like a k by k matrix representing the loss function, where k represents the cardinality of the output space G. Cardinality basically represents how many number of classes that you have. Suppose if you have two classes, then it becomes a 2 by 2 matrix. Getting it? Depending on how many number of classes, how many number of discrete values that are the space has. So that represents the k. Correct? So now how it looks like, here is an example, of course, given. Suppose k equal to 3, that is 3 classes, then loss matrix looks like it's a 3 by 3 matrix, and the matrix is such that all the diagonal elements of the matrix is 0, indicating that it's a correct classification. See, in any matrix, if you look at, okay, there are 3 classes, suppose, say, that is G1, G2, and G3 are the 3 classes, suppose, say. In the row, that is a column wise. Similarly, row wise, G1, G2, G3, let me write. Now, if you look at this, the diagonal element, all the elements in the diagonal, it represents the correct classification. G1 mapping to G1, G2 mapping to G2, G3 mapping to G3. Here G1, G2, G3 represents three different classes, right? So it's a correct classification. So if you indicate that these diagonal values are 0, so that means here I have diagonal values of a matrix K by K is 0, I said. What is the meaning of it? Its meaning is it represents the correct classification. It is indicated by the loss value is equal to 0, loss factor or weight, or you may call it as a cost. So that is 0. That means it's a correct classification. That's the meaning. So the entries in the matrix, so if you call it as a loss matrix here, so the entries in the matrix, that is L of K comma L. So K represents the number of different rows here, corresponds to different rows. L represent the columns, K comma L, row comma column. Correct. In the loss matrix represents the cost incurred in classifying K as L. So the entry here, for example, whatever the entry that you do here, so this entries represents the loss incurred in classifying K as L. That is G1, G1 as G2, G1 as G3, and so on. That is a misclassification. So for each misclassification, we give certain weightage. So that's basically the we look at how the loss function looks for a classification problem. So it's totally different from what we had seen earlier for the case of regression, where it was simply a squared error. Okay. Now, so one of the loss function, as I said, the K by K matrix, one of the loss function that we can have is simple one is a 0-1 loss function. It is called as 0-1. So 0-1 loss function. Okay. So it's a most popular loss function that we have. It's sufficient, of course. With this simple loss function, we can manage many of the classification problems. Right. Let's consider this example to understand what is this 0-1 classification. Suppose if you the same previous case, say G1, G2, and G3 are the three classes. Okay, let's consider three classes, and I'm considering the 0-1 loss function. So how the 0-1 loss function looks like? So it's exactly L of this is of the form L of K comma small l. So K indicates the rows here. K is indicating the row, L indicating the columns. So here K 1 1, let me start the index by 1, right? So 1 1 is a 0, indicating G1 is classified as G1. It's a correct classification. Loss is 0. And G1 is classified as G2. Okay. So that means there is a loss, or this loss is indicated by a weight is equal to 1. So whenever a particular misclassification happens, one class is assigned to another class. So that is assigned with the loss value or cost of that as 1. Okay. So therefore these entries becomes 1. Rest of the entries becomes 1. So zeros only in the diagonal and rest will be 1. So that's how the loss function looks for a 3-class problem or 3-class output. Say with the G1, G2, G3 are the outputs. G1, G2, and G3 are the outputs. Okay. So here, let me make it clear. 1 represents what? Entry 1. Entry 1 represents the misclassification or correct classification. It is a misclassification. and 0 represents correct classification, and 0 represents right class. Okay. I hope point is clear to you. So the cost of wrong classification is 1 and cost of right classification is 0. Therefore, you have only zeros and ones in the matrix. It's like a binary, zeros and ones, and therefore it is, of course, that's the reason why we call it as a 0-1 loss function. Okay, 0-1 loss function. Now coming to the, how do you estimate, or what is known as our famous expectation of prediction error, is not? So expectation of prediction error in this case, if you look at, so first it is nothing but expectation of the loss function, is not? Expectation in the previous case also we have seen that. So earlier case it was loss function was a squared error. Loss function was squared error. So expectation of squared error we have seen. But in this case, the loss function itself is, it is now denoted as L of g comma f cap of x. So I have denoted this earlier. So look at this. Loss function is denoted as, so here, yes, yeah, L of k comma L, small l. So here what k denotes? K denotes is the true class and L denotes the output class to which it has been classified. True class is K and it is classified to as L. So K comma L, that's the meaning. So here L of g comma f cap of x, what does that mean? So capital G represents a random variable of the true class. It's supposed to be, see, when you give the x as an input, we expect the output to be the g, and the difference that is represented by the loss function, that is L of g comma f cap of x. So here f cap of x is the output estimate for the given x, or the prediction of the output when the input is x. Okay, prediction of the output when the input is x. Hope that point is clear. Equation 1. So we wrote. Now let us try to obtain, bring the concept of probability now, because there is an expectation, right? So if you want to evaluate that, then I need to know what is the associated distribution function. What is the associated distribution function? I need to know, right? So very similar to the regression case. What was the regression case? The distribution function that we have assumed, that is the joint probability. If you remember, from the input data space, we have written the joint distribution function, PDF. But it's not the case in exactly the case here, because output is not discrete. Sorry, output is not continuous, it is discrete. Because the output is discrete, so you understand, it becomes joint probability, it becomes a probability value. So their integration becomes summation here, that we'll see next. So we can write EPE, that is the expected probability of error of f cap. So it does not mean that it's a function of f cap. So it's a probability of that, that's the meaning. So that is equal to, so you can split the above into two parts. So what we are doing to do here is very similar to what we have done earlier. So we are writing by using the basic probability rule, that joint probability of x and y, we can write it as joint probability of the input and output can be written as joint probability of the input into conditional probability of output given input. That's what we have done here. So in terms of expectation, it becomes expectation of x into it becomes the product there into expectation of g given x. G is output there, given x. Okay, so again it's like evaluating point wise, conditioning point wise on the input. Okay, so expectation of g given x of a loss function, that is g of f cap of x, given that it is x, or you can write x is equal to x. It doesn't matter, x is equal to, for x, capital X is equal to x. Capital X represents the random variable and small x represent a particular input point. Okay, so that's equation 2. So but the loss function is a discrete function, as I already, so distribution is discrete, so therefore we can write this equation, the expectation, conditional expectation g given x by using the summation, is it not? So this conditional expectation can be given as summation of this loss function, the same loss function that you have, into the probability value. It is not probability density function, it is simple probability, but it's a conditional probability rather, because you are using a conditional expectation, so it has to be a conditional probability. So what the conditional probability here indicate? It is a probability of k given x, means what is the probability of choosing the kth class given that the input is x, or capital X is equal to x. Okay, how many number of outputs classes that you have? Small k represents the variable here, which is running from 1 k equal to 1 up to capital K. There are capital K number of classes that you have. Now this loss function L can take, which are the values that it can take? If you think of a 0 1 loss function, for example, then it can take either 0 or 1, right? Because L of k comma f cap of x can have either 0 or 1, and into the probability. So sum of that, if you do it, then we'll get this conditional expectation, and if you substitute that conditional expectation in the previous expression, so you'll get the EPE, correct? So EPE of f cap rather, because we say the estimate, so that is equal to expectation of x into the summation in equation 3. So this equation 4 is pretty clear. So now this is what we have computed in equation 4. We have computed the error probability or expected error probability of error, and our intention is to come out with a function f cap or estimate of f such that it minimizes this, is it not? To minimize, the objective is to minimize such a way that, objective is to find out the value of f such a way that it will minimize the EPE. So here this I have mentioned already. Here k is the true class and f cap of x is the predicted output for a given input x. I hope these notations are clear by this time. If you have any clarification, you can stop me. Okay, now what we do here, we try to obtain the f cap by putting a condition. So now the condition is the argument minimum. You can recall the previous case again. Now argument minimum with respect to some c we did, f of x we did, right? But now it's something output is g here. We denote it as g here. So what we are going to do is, in the minimization, when you do this equation 4, so we have to really look at only the summation part, right? Because minimization, when we do with respect to, minimization of the RHS, then there is no role to play. Expectation of x has no role to play, right? Because that's simply represents the expectation of the input, which is constant. Okay, so therefore the minimization argument, so what you have is only the summation term. So this summation term with the k running from 1 to capital K, So we are trying to minimize for every G. So what is the meaning of that? So you take a point, input point X, and find out what is the loss associated with that X. That is, you have a G as output, and for all such points in input X, you compute. Okay, so the loss, when it is, loss function has to be calculated for all values of K, with K equal to 1 to capital K. Okay, and get the summation. Okay, this summation, product of sums, and that you take the minimum of the all possible values, such possible values, of I mean against G. So for one G, you calculate for a particular value of G, like G1, G2, G3, and so on. So whichever gives the minimum, so you choose it as a output. So by doing that, for all possible values of the input, you will get the function f of x, or rather estimate of f of x, that is f cap of x. So this is very similar. It's sounds, I believe, you can compare with the previous discussion that we had. Okay. Only thing is that you have to understand that it is a discrete. Okay. Very similar to the regression case. That's what I said here. Just given a statement here. Equation 5 implies that the select a value G such that it gives the smallest expected error for a given input data point X. Okay. Smallest expected error. Okay, that's what we do here. So in order to elaborate this, if you do that, you can take some examples here. I have an example here. You have any questions till now? It's 9:30. Okay. Okay. Fine then. So just let us look at one example and then I'll stop. Okay, fine. Consider this example. It's the 0, 1 loss function for a 3-class problem. Very similar to what we have seen earlier also. Let's assume that the probability of G1 given X is some 0.6, probability of G2 given X is 0.2, and probability of G3 given X is 0.2. So you understand that total probability is 1. So this is a given problem where G1, G2, and G3 representing these 3 classes. These are the class labels we call it as. So you construct a loss function and find the error scores for each class. So that's the problem. So this is your output data set, output set, that is G1, G2, G3, 3 classes. What is the capital K represents? Capital K is equal to 3 number of classes you have, K equal to 3. So your summation here in the above run from K equal to 1 to 3, right? So we have to compute for K equal to 1, 2, and 3. And what about G here? It can be G1, G2, or G3. Only 3 possibilities, right? Because only 3 classes you have. Now the loss function, try to write down. Writing loss function is very simple. It's by this time you must have very clear about this. So what actually the row represents? The rows are say K's, and columns are represented by K comma L, is not? So this is a G1, first one, G2 or G3. And similarly here, G1, G2, G3. Okay. You may consider one as the input side, the other was the output. Right. If G1 is the input, if K is G1, then the loss incurred when it's classified as G1 is 0. Otherwise, when you classify it as a G2 or classify as a G3, then the loss is 1. So similarly, the other cases. So that's how we construct the loss function, and this is your 0, 1 loss function. 0, 1 loss function. Okay. So we have the score for classifying the input. So input X as a G. So you are classifying the input X as a G. When the true class is K, so actual class is K, you have you have given the value X is equal to X, is not, from the input, given that it is X is equal to X, you take X, small x, and now you compute the score corresponding to classifying it as the given input as G when the true class is K. Actual class is K. You're classifying it as G. So G may be one of K also. That's possible anyway. So what is the score? So score is calculated by evaluating this summation. So say for example G equal to G2. So G can take only three possibilities, right? Either G1, G2 or G3 in this case. So suppose say G equal to G2, then what is the loss function here? L is either 2, 2, 1, 2 or 3, 2, is not. So K can take only three values, 1, 2 and 3. So the output is G2. So L of 2, G2, which is your G2 input is G2 and the output is also G2, right? So true classes and the expected output is same, so it is 0. 1, 2, that is true classes K and output you have classified as G2. Then it is wrong. Actually 1, the score or the loss is 1. Similarly, L of 3, 2 is also 1. Hope you can get that. Now if you substitute and simplify, we have already been given the probability of G1 given X. What is the probability of classifying it as a G1 given that it is X? It's given in the problem. Yeah, it is 0.6. And G2 given X is 0.2 and again 0.2, right? So using that, you can simplify, you understand that it is equal to 0.8 total. Second is 0 because L of 2, 2 is 0. So next is you have 0.2, otherwise, so L is either 1 or 0, right? So it's simple. So you'll get 0.8. So if you consider G equal to G1, then you understand L of 1, G1 is 0, other two is 1. So it's in this case score becomes 0.4. Correct? The first one is 0, the second one and the third one. So you get 0.2 plus 0.2, that's 0.4. Correct? And for G equal to G3, the score is 0.8 again. Correct? Because what is 0 there? 0 is corresponding to 3, it is 0. L of 3, right? So you understand that the scores. So which one you actually classify? The one with the score minimum or maximum? The score with the minimum, right? So your objective is to minimize this. So which one is the minimum here? 0.4. Score is minimum. But what is the probability corresponding to that minimum? Probability is maximum. Just observe that. Score is minimum. Corresponding to that, the probability is, if you look at, it is 0.6. G1 given G1 given X. It is 0.6. Probability is maximum. Are you getting the point? So you are classifying it as a G1 because the score is less among that. 0.8, other is 0.8, 0.4 here. The score is less, therefore you are classifying it as a G1. But now look at the probability, given probability. So given probability is maximum for G1. What does that mean? Given an input, the probability that you get a class G equal to G1 is maximum. So it is our simple, you can just change this argument here in this equation 5. Instead of taking argument minimum, you can choose argument maximum with respect to this probability of k given x, not with respect to g now, but with respect to k, with the k varying from 1 to capital K. I hope you are making the able to grasp the point here. So that what the statement made here. Observe that the minimum score corresponds to the highest probability, that is probability of g1 given x. Therefore, we can rewrite the statement argument minimum can be written as argument maximum in that equation 5 which I just shown. So that is f cap of x can be simply written as just maximizing the probability of g given x. Is it not very simple now? Looking very simple. Just you are maximizing the conditional probability. Of course, I have written here purposefully g or k, whatever it is, variable. Fine. Now, whatever this we have done in equation 6 that you see here. So this is a very well-known classifier called as Bayes optimal classifier. It's known as Bayes optimal classifier. Okay, so anyway, it's I think in 40 I'm taking more than my capacity anyway. Any doubts? Fine, let me just download the attendance.